So today we'll talk pipeline that was talked about yesterday was essentially an in-order pipeline, right? So when I say an in-order pipeline, what do I really mean? What do I mean when I say an in-order pipeline? You guys have, how many of you have taken an organization course before? Okay, all right, so you're familiar with the terminology at least, if not the exact functionings, right? So terminology, in-order pipeline, sort of everybody's kind of heard of. All right, so in-order pipeline, what does that mean? Yes, sir.
Instructions are processed in the way they're written.
In the way they are written, all right. Okay, so that's part of it, right? Why would we not want to have in-order pipeline? Okay, or a better question to ask is, what are the shortcomings of an in-order pipeline? So in-order pipeline, something, sorry, what's your name? Anurag. What Anurag said is somewhat correct, right? So a program is a sequence of instructions. Instructions are fetched from memory, fed into the pipeline, they graduate. And in the pipeline that was talked about yesterday, you fetch an instruction, it goes into the pipeline, and the next instruction follows it, and the next instruction follows it. They come out of the pipeline in the order they got into the pipeline, right? So if instruction 1 got out of the pipeline at some point in time, it will come out first. Then instruction 2, who got in after instruction 1, is going to come out, so on and so forth, right? And in the program, instruction 2 is after instruction 1, instruction 3 is after instruction 2, and so on and so forth, right? Okay, so this is what we have right now, right? We have an in-order pipeline where we have instructions 1, 2, and 3 who go into the pipeline in the order of instructions 1, 2, and 3, and they also come out of the pipeline in the order of instructions 1, 2, and 3. Okay, this is what we have. Can we do better? Yes? Or is this good enough? Right? We can do better. All right. How can we do better? What would you do in order to make sure that we do better? Okay, so let's not go there yet, right? But let's keep it to a little high level, right? Am I giving you enough information when I say you can do better? Is there something that you need to ask me to actually answer that question? I said, can you do better than an in-order pipeline? Isn't that a vague question? Sorry? What's the problem? That's absolutely correct, right? When I say, can you do better? It's like, what do you mean, can you do better? Right? What do I mean by better? What does better mean in this case? So I have an in-order pipeline. I have a set of instructions that flow through the pipeline. And I want to do better, right? What does better mean here? If I was to pick a metric for better, what would that be? Sorry? Throughput. Who said throughput? Yeah, good. Okay, good. Throughput is the metric that I want to do better on. What does throughput mean in this case, in the case of an in-order pipeline? Sorry, one at a time, please. Somebody from here? Yes, ma'am? Can you just speak out a little louder? Number of instructions per cycle. Very good, right? So in an in-order pipeline where we had instructions 1, 2, and 3 going into the pipeline in order and coming out of the instruction pipeline in order, assuming that each pipeline stage, which is let's say 5 stages, takes 1 cycle each, what was the number of instructions per cycle in the best case scenario that I could have potentially gotten in that case, in the case that I was talking about before? 1 instruction per cycle, right? 1 instruction per cycle is pretty much the best I can do. What I want to do is better, right? I want to do better. I want to increase the throughput. I want to have more than 1 instruction per cycle complete, right? So that is what I want to do. When I say I want to do better, is essentially what I mean is I want more instructions per cycle to complete, right? Why is that better? Throughput is a metric. I want to optimize throughput. What happens if the throughput increases? I go from a throughput of 1 instruction per cycle to 1,000 instructions per cycle. What does that mean? Absolutely, right? So in an ideal world, if I go from a throughput of 1 instruction per cycle to 1,000 instructions per cycle, technically my execution time will come down by 1,000x essentially, right? So that's essentially why we want to increase throughput, why we want to increase the number of instructions that are being completed per cycle of the clock. Right? That's essentially the overall bigger picture. The bigger picture is increasing throughput and decreasing execution time. All right, and the question now is how exactly do we go about kind of doing it, right? So one of the first things that we need to talk about is essentially what is known as program order, right? And before we get there, let's talk about programs. Programs. Why do we write programs? Everybody's written a program here, right? Everybody's written a program? Anybody who's not written a program? Okay, good, thank God. Why do we write programs? Sorry? To do meaningful work. Absolutely correct, right? So you write a program because you have a problem that you potentially cannot solve with pen and paper, right? You write a program and you sort of code in a sequence of steps that a program should do in order to solve that problem, right? What essentially that means is you have thought about a sequence of steps and then you have coded them up in that order. Ki pehle this should happen, the next thing is that this should happen, the third thing, the fourth thing, and that's when I'd call my problem solved, right? Now, it's important for you to solve the problem is that these steps happen in this exact same order, right? If step 5 happens before step 2, then your problem is not actually solved because you need your problem to be solved sorry, in a certain way, right? So you need step 1 happening first, then step 2, 3, 4, and 5. This is essentially what program order is, right? So you want to solve a particular problem. The problem has a set of sequence, a set of steps. The steps need to be taken in order. And it is important for you to solve the problem correctly that those steps actually happen in order and steps don't happen out of order, right? But that sort of contradicts what we were talking about before, right? What I was talking about before was essentially we have to increase throughput. We are going to do that by doing sort of out of order processing. But now that violates what I just talked about program order, right? You have this program order of steps that need to be executed. So how do we reconcile these two things? The one thing is I want to increase throughput by executing things out of order. The second thing is I want to preserve program order, which is essentially the sequence of steps which your program does, right? So that's the part of this entire lecture where we talk about is one thing, one goal is we want to maximize the number of instructions that we want to execute per cycle, which is out, and one of the ways we can do that is by executing instructions out of order. And the second thing is that we need to preserve program order, which is essentially the sequence of steps that need to be executed by the program in order to the program or in order for the program to solve the problem correctly, right? So let's go through a few slides. By the way, any questions up until now? Problem is motivated correctly, right? Now, this is what most of 90s and up until mid 2000s were spent in computer architecture, right? This is what people were trying to optimize for, right? Going from an in-order pipeline that executes one instruction per cycle to going to a pipeline that executes more instructions per cycle, right? So, okay. So we've sort of talked about most of this anyways, right? Okay. The one thing that we haven't talked about is essentially this is a very simple 5-stage pipeline, right? We've seen this before. Okay. One of the few assumptions that were made in this pipeline was the fact that each one of these each one of these stages takes an equal amount of time, right? So we say it's a 5-stage pipeline. Every stage takes one cycle each. Is that always correct? Is that a fair assumption to make all the time? That every instruction takes one cycle? No, right? Okay, that's a fair point. Which of the pipeline stages might take more cycles than one? So somebody from here? Memory. All right. What else? Sorry? ALU? Okay, that's a fair point. How? Absolutely. Like what? Absolutely right, right? So this stage, which is essentially just being pointed out as the ALU stage over here, this ALU could essentially be an add, it could be divide, it could be a multiply, and depending on how it's actually implemented, an add could be done in as little as 1 cycle, a multiply could be done in 5, 10, 15, 20, whatever, how many ever cycles. Similarly, a divide, right? A divide could take 15, 20, 25 cycles, that is. Okay, so that can happen, yes. Uh-huh. So, okay, that's a fair point, but what do you mean by a non-balanced pipeline? Okay, and how is that a problem? That is true, right? So, but that is sort of how instructions are processed as well, right? In the sense that okay, so we have to make the assumption that not all instructions are going to take the exact same amount of time, and you are right that it is going to make it an unbalanced pipeline, to use your terminology, but the deal here is that that is going to happen anyways, right? A multiply is going to take longer than an integer add, and the idea here is how do we actually make pipelining to work for us, even with that assumption in place, right? So that is true. Unbalancing, so to say, is going to happen, and then we'll take a look at how we can go about doing things even with the unbalancing happening in place, right? Okay, so in this stage, what we are, or from this point on, we are going to assume that this ALU stage is actually going to take can potentially take variable number of cycles, right? So 1 cycles, let's say for an integer add, excuse me, and more cycles for different kinds of operations, right? So, okay, so potentially the pipeline can look something like this, right? So in this case, I have, and I'm sorry for the poor quality, I hope you can read it somewhat. So this is instruction fetch, instruction decode, and at this ALU stage, now you have multiple types of instructions that take multiple or different number of cycles. You have potentially a memory instruction or memory stage over here, and then a write back stage over here as well, right? And now, depending on what kind of an instruction you are pushing through the pipeline, it might take different number of cycles. Here it is an integer add, here it is an FP multiply. So integer add takes 1 cycle over here, and FP multiply takes 1 to 7 cycles over here, and similarly a divide operation takes probably around 25 or 30 cycles, right? So this is how things are assumed to function. Some operations takes longer than the others, and that complicates the design of our pipeline. So this is sort of the first assumption that we'll make in the design of out-of-order process, is that initially what the assumption was, every stage takes 1 cycle, so everything comes out one after the other. Now, if we change that assumption to say that, okay, each one of these stages is going to take different amounts of time, does that create an out-of-order pipeline? That's the question here, right? So we have changed the assumption. ALU stage takes varying number of cycles now. Now, does this lead to an out-of-order processor? Just changing that assumption over there. I'm going to take a poll. How many say that this is going to lead to an out-of-order processor? 2 people. Anybody else? 3. Going once, going twice, 4, 5. All right. Am I asking the right question when I ask, is it going to lead to an out-of-order processor? What does that mean? What do I mean when I say it leads to an out-of-order processor? Anybody? Yes. A later instruction can finish earlier than the earlier one. Absolutely right, right? So a later instruction can finish earlier than an earlier one, and that leads to an out-of-order processor. Is that correct?
But it depends. If it is not there, it will not be there. If some dependent instruction is there in the program, then it will not be execution.
So give me an example as to what can happen. So you are sort of on the right track, but tell me what exactly. Can you be a little more precise?
Like we are doing addition over a single variable in a loop.
Okay.
So the value of the current variable
Mm-hmm.
will lead to the next variable value. Because if we are going on the same variable,
Okay.
the value of the same variable.
Okay.
So how we are going to do it in order
Right. So that part I absolutely agree with, that not all sequence of instructions can lead to out of order processing, right? But in this particular case, so yours is a very special case where it will not happen. All right, that's granted, right? But are there cases? So a program could be a whole bunch of or a sequence of instructions where not similar types of instructions would be followed by one another, right? So an FP multiply could follow an integer add, or an FP divide could follow an integer add, and things like that. And in situations like this, like they happen in real programs, right? So you might do a divide followed by a multiply or something of that sort. In that sort of a program and this kind of an assumption, would that lead to out of order processing? Yes, right? Anybody kind of disagrees with me right here? No? Okay. So even if they are completely independent, there could be out of order processing, right? So that's actually a good point. So let me sort of try and give an example, right? So I have an instruction 1, and let me see if I can write here somewhere. So if I have an instruction 1, which is, let's say, an integer add, right? So what is the path of an integer add in this pipeline? So let's say instruction 1 enters this pipeline over here in cycle 1. It goes through fetch, decode, execute, memory stage where it does nothing, and then it goes to the write back stage. So these are the 5 stages in the pipeline that an integer add will follow, right? Let's assume that I wrote a very silly program where an integer add is followed by an FP multiply, right? An FP multiply, what is the path of that particular instruction? It goes through fetch, decode, then it goes to these 7 stages of the FP multiply, then it goes to the memory stage and the write back stage, right? So if in the best case scenario, my instruction 1 was entering the pipeline over here, which was an integer add, it will go all the way and finish at which cycle? Cycle 5, right? So it will finish at cycle 5. And if in cycle 2, my FP multiply is entering the pipeline over here, so cycle 2 it goes here, cycle 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right. That's a bad example why of what I was trying to talk about. Because in this case, the second instruction is finishing after the first one. But if these cases were reversed, right? If my integer or if my floating point multiply was the first instruction to go into the pipeline, and then the integer add came in, right? Is that going to be an out of order pipeline then? So the first instruction that goes in the pipeline is an integer multiply, or sorry, a floating point multiply, and the next instruction that goes in is an integer add. Now, is this out of order, given what we have just talked about so far? It is, right? It is because, right, so the add will follow the exact same path that we talked about before. It goes here, comes out here, add it comes out potentially in cycle number what? Assuming there are no hazards, assuming there are no dependencies, instruction 2, which is an integer add, enters the pipeline in cycle 2, potentially comes out in cycle 2, 3, 4, 5, 6 over here, and FP multiply goes in cycle 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Right? So this is essentially an out of order, sort of becomes an out of order pipeline, right? And is this a good thing in terms of program order? Yes.
So out of order actually includes both the cases wherein like instructions are scheduled out of order and also when instructions are completed out of order.
Right.
Both of them include out of order.
It does, right? So, and we'll add that complexity later on as well, right? So, but for the time being, the assumption is the instructions enter the pipeline in order, but they complete out of order. But you're absolutely right? I mean, there are two things to here, to that case as well, right? But for the time being, to keep things simple, instructions enter the pipeline in order and hopefully complete in out of order, right? Okay. So, all right. So, what I was asking was, now that instructions are completing out of order, is that a bad thing or a good thing as far as the program order requirement that we talked about before, right? So everybody's sort of clear about program order, what program order is and why program order is kind of necessary. All right, so let's do a quick rehash. What is program order? Anybody from over there? Program order is, sorry? The way we have written the program. Sequence of instructions, right? Sequence of instructions that I want to execute in a certain order for my program to give me the correct behavior, right? So I wrote a program that essentially gets compiled into a sequence of instructions, and they have to be executed in that sequence for my program's output to make any meaningful sense. This is what I absolutely have to preserve, right? Now, given these assumptions, things are happening sort of out of order. Is that good or bad from my program order constraint, or preserving the program order constraint? It's good if it's not changing my output. All right. Okay. So yeah, that's one way to put it, right? So as long as this happens, as long as this can happen while my program order is being preserved, right? So then essentially I can do all the optimizations that I potentially can, right? So which essentially is an interesting point in the case of an in-order pipeline. So we have this concept of program order, right? And then we had the concept of in-order pipelines. Was program order preserved in in-order pipelines, right? So what you can assume is inherently program order is preserved in in-order pipelines, because until and unless instruction 1 sort of goes out of the pipeline, instruction 2 cannot go out of the pipeline, right? So instruction 2 is always going to follow instruction 1, instruction 3 is always going to follow instruction 2, so on and so forth. So in an in-order pipeline, program order is inherently preserved. That is not the case over here, right? So if I make this assumption that my different operations take different amounts of time, my program order constraint is not going to be preserved. So now I have to make sure that my program order constraint is actually preserved, right? And then we'll talk about how do we actually go about doing this, right? So but we'll try and formalize a little bit in terms of what are the problems that can happen when we relax the assumption that my ALU stage is not going to take multiple cycles, right? So let's go over the problems first. The first one is potentially multiple writes to the register file is what I have written over there. Okay. So this is what it says over here. Potentially multiple writes to the register file. Is this going to be a problem in this case? Come on. Okay. Can that happen? Multiple writes to the register file at the same time. In this sort of a scenario, can that happen? Yes, right? How can it happen? Anybody want to give me an example of how this can happen?
Completing like FP multiply and it's completing one operation at the same time 11 integer additions can complete.
Absolutely right. So let's say you're at cycle 11. This is the cycle where the FP multiply is trying to write its output in the register file, and some earlier instruction also completes. Let's say there was this long-standing divide that completed at cycle 11 as well, or cycle 11 is a bad example. Let's say cycle 55, right? Cycle 55, a floating point multiply completes, tries to write its results to the register file. At that same cycle, a long-standing division also completes. You're trying to write to the same register file. That is sort of a problem. That is also known as what Lavanya talked about yesterday as what kind of an hazard? So structural hazard, exactly, right? So you have this one shared resource, which is your register file, and now you have multiple sort of instructions trying to write on the register file, right? How do you remove structural hazards? In this case, how would you try and remove this particular structural hazard? Multi-port register file, absolutely right? So rule of thumb, one of the easiest ways of trying to of avoiding structural hazards is throwing more money at the problem, right? So basically you have a register file, you have only one read and one write port. Oh, I have multiple instructions trying to write to this register file at the same time. What I do is essentially give it another write port, right? That's the easiest way of solving it, and that's sometimes, or a lot of the times, it actually works. A lot of the time it doesn't. But in this particular case, where you have multiple operations trying to write to the register file, this absolutely works, right? Okay, so that's one problem. Frequent raw hazard. So anybody's heard this particular hazard before? RAW, which is which one? Read after write. Absolutely right. So there is a read after write hazard that's going to happen in this particular case. So let me try and write this down a little bit, right? So read after write hazard happens when we have a register which is writing into register R1. Okay, this one doesn't work that well, so let's try this. There is a register R1 that is being written into, and then there is a read from register R1. So there is a write over here, and then there is a read over here, right? And this is a read after write hazard, right? Okay. This type of hazards can happen in this particular pipeline. Is that right or wrong? Oh, sorry. Should go back to this slide. Read after write hazards. You have register R1 that's being written to over there in this particular. So and again, you can think of these instructions or these things as instructions, right? So this is instruction, let's say 1. This is instruction 2, right? So these are the kind of hazards in which you have true dependencies between two instructions that are following each other, right? Okay, so if you have situations like these sort of situations need to be handled well in this kind of a scenario, right? So how are the read after write hazards going to, so everybody sort of understands read after write hazards, right? And how is that going to create a problem in this pipeline order over here? So the assumption is I have this thing over here, right? The ALUs, depending on what you're doing, take different amounts of time. How are these read after write hazards going to create a problem here, or a true dependency? Okay, say that again.
The write stage happens to be the last time of the execution of the pipeline.
Right.
And the read stage has to be done sometime later before you get into the execution.
Okay, that's somewhat on the right track, but these are two different instructions, right? So two different instructions. The second one depends on the output of the first, and the assumption here is that each one of these stages takes different amount of time to process, right? So in this case, true dependencies might create a problem, right? True dependencies between instruction 2 and instruction 1 is going to create a problem. Why? Exactly, right? So it goes back to the same sort of an example. So what's your name? Newton. All right. So what Newton pointed out is absolutely correct, right? So for example, if this instruction, the instruction 2 over there is, for example, and again, I'm taking examples that might not happen, but if that instruction is an integer add that wants to read R1, and if the first instruction R1 or the first instruction is a floating point multiply that takes longer, or even if you want to make it even worse, then there is this floating point divide, right? So this floating point divide writes that instruction in cycle number 35, whereas the instruction 2, which is an integer add over here, entered the pipeline and wanted to read the instructions in cycle number 1, 2, 3, or cycle number 2 actually, right? So, or 2 or 3 depending on where you want to implement registry. Okay, so this is going to be a problem assuming different cycle times for different instructions. How do we get over that? What is the simplest kind of a mechanism in order to get over this sort of a problem? Okay, so assuming, okay, let me clear the assumptions. These are the two instructions in the pipeline, right? There is going to be a problem. Instruction 2 depends on the output of instruction 1, right? And I want to make sure that it cannot proceed until and unless this guy has written its output into R1, right? So what would I do in this pipeline for instruction 2 such that I can sort of honor this dependency? I can write it to a different register. All right, so I would have to do some sort of compiler optimization where I have to rename these registers, and we'll talk a little bit about that as well. In the simplest case, assuming I can't do fancy things like that. Sorry, what's your name? Anurag. Sorry, I'm going to keep asking until I remember. All right, so assuming I can't do fancy things like that, what is the easiest thing that I can do? By instruction 2, I could just make it wait, right? I'd say, well, until unless your result that you need to proceed is actually available, just wait until that long-standing divide actually completes, right? So that's one way to handle. And okay, so one way to handle this problem. Where can I potentially make it wait? So I have these different stages in the pipeline. Where can I make this instruction wait? What would be the best stage in the pipeline to make this instruction wait? Huh? Before execution is the decode stage, right? Why in the decode stage?
Because it will be needing the data at the execution stage.
Okay.
It needs that data which is going on with, for example, the divide.
Okay. What else will it know at the decode stage? What is the information that it needs to know at the decode stage so that it knows, okay, I have to wait in this stage now? Absolutely right. What's your name? Poonam. All right. So what Poonam said is absolutely correct, right? So what it needs to know is that I need the result that's going to be written in R1, which is essentially going to be written by this multiply that has been scheduled in cycle number 10. I'm at cycle number 15 right now, so I have to wait these many number more cycles before I can actually proceed, or before the results of that earlier operation are going to be available, right? So it needs to stall right here. So essentially a stall is nothing but, are the operands ready? Yes or no? Are the operands ready? So it's sort of like busy waiting. If you want to sort of visualize a stall over there, you can just think of it as busy waiting in the decode stage. All right? Okay. Then write after write hazards, right? So write after write hazards are also possible in this in this pipeline. So what is a write after a write hazard? I have instruction 1 that writes into R1. I have instruction 2 that also writes into R1, right? Why is this a problem in this case? Yes, sir. Huh. Not really if you make it wait, right? So the idea is that instruction 2 is dependent on the output of instruction 1, and if I'm making the instruction 2 wait until unless that output is actually ready, then I'm sort of getting rid of the hazard, right? If there, you can have cases where you could read the wrong value, and we'll take just a look at this in this case. Yes? That's one way of doing it, yes. Yes, I mean, the whole idea is to make sure that dependencies are preserved and program order is preserved, right? How you go about doing it is a couple of things that we'll also look at.
So read after write hazards only occur if there are dependencies between the two instructions.
So yes, that's a true dependency, right? So what we talked about in the last case was essentially true dependency where the instruction 2 actually needed the output of instruction 1. There are cases where, well, read after write hazards only happen in the case of true dependencies, yes. There was one more question over there. Somebody else? All right. Any more questions so far? No? Okay. All right. So let's take a look at okay. Write after write hazard. So in this case, we have this particular example where I have instruction 2 that writes into R1 and instruction 1 that also writes into R1. And again, by convention, we are going to assume that instruction 2 follows instruction 1. Is this going to be a problem in this sort of a pipeline where I have different, okay, where I have, come on, different instructions going through the pipeline and taking different amount of time? Can anybody think of a situation where this sequence of instructions, can potentially create a problem for me? And when I say a problem for me, I mean program order, right? Violating program order. right? Okay, so that's, what's your name? Aditya. So what Aditya pointed out is essentially going to be the kind of problem that we can sort of assume in this case, right? So let's say I have an instruction which is writing into R1, and let's say it's an integer add, right? It's an integer add, it writes, or, okay, so let's assume this is a floating point divide. This instruction 1 is a floating point divide. It writes into R1 the number 30. Okay? This is my instruction 1. The next instruction that follows is an integer add, and it writes the number 55 into R1. Okay? Well, actually, so let's go with this example. It might be a correct example, it might not be a correct example, and I would need you guys to point it out, right? Now, I have an FP divide writing 30 into R1, an FP or an integer add writing 55 into R1. The next instruction that's coming over here, I3, which tries to read R1. What is the value of R1 that it should expect, assuming that I want to preserve program order? Sorry? 55, right? Okay. So, if I was to give you an example of a write after write hazard, is this the right example to go with? It's not. What would I have to do with these sequence of instructions to make it a write after write hazard? Example of a write. You guys know. All right. So if I reverse the order of instructions, right? So if I say that this is an integer add, and I make this a floating point, what was it, divide? Okay. If I make this a floating point divide, now it's a problem, right? Now it's a problem for the instruction 3 over here. Why is this a problem for instruction 3? Exactly, right? So if we don't preserve the dependencies properly, let's say this instruction takes 30 cycles to complete, right? This instruction takes 30 cycles to complete. This instruction takes 5 cycles to complete. If I let this instruction complete before this instruction, what this guy gets is the value 30, right? Which essentially should not be the case for my program order to be preserved, right? So we have to find a way to somehow manage those dependencies as well, and we'll see how that can happen. So the other thing that I want to sort of just talk quickly about is what is known as exception support. So anybody knows what exceptions are? Can something go wrong when instructions are executing? In this particular case, right? You have a whole bunch of instructions that are flowing through the pipeline. You have multiplies, you have divides, things like that. Can something go wrong? Let's say a multiply or a divide is going on. Divide by 0 can happen, right? Or some other exception in your floating point multiply might happen, right? That can always be the case. Now, let's say you have a case where you have a divide, long-standing divide, which is eventually going to be a divide by 0, right? Happening, and then you have a whole bunch of instructions that are following it, which are all, let's say, integer adds and subtracts, right? So you have a divide, then add, subtract. Now, divide is going to fail at cycle 30 because that's when it completes. In the meantime, all these different adds have completed because they only take 1 cycle each, assuming there are no dependencies, right? Is that a problem for my architected state? Absolutely right? So if there are dependencies between instructions, then there potentially could be a problem, right? So what I want to do is, if a long standing instruction, which is either a floating point multiply or a floating point divide, has some problem somewhere before it can actually complete, what I want to do is go back to the state of my processor where that instruction might not have happened, right? So anything that follows that instruction, that instruction state should not be committed. So for example, if I take an example of again instruction 1, 2, and 3 as being let's say this being a divide. Is this visible? No. Okay, let me try this. So I have, this is better, right? Okay, I1, I2, I3, this is a divide, this is an add, and this is also, let's say, an add, right? So if I had a divide which is essentially going to be a divide by 0, then I have these two adds happening over here, which essentially would complete relatively very fast, right? But that divide is going to fail in, let's say, cycle 25 or cycle 30. At that point in time, when it fails, what I want my process state to reflect is everything that has happened up until this point in time over here, right? These instructions should not have potentially completed, right? Because everything that has happened only till that point. Then I'm going to sort of restart using some exception handler or something of that sort, right? So I need support for that to happen as well, right? Because what could potentially go wrong? So let's say I have a case where I have this divide, that is a divide by 0, failing in cycle, let's say 30. This completes in cycle 5, this completes in cycle 7, right? What could potentially be the problem if I lead instructions 2 and instruction 3 to actually write their state into the register file? All right, so let me try and make it a little more concrete. Let's say this writes into R1, right? This writes into R2, and let's say this reads from R1. So this instruction reads from R1, this writes into R1, this writes into R2. This is the example instructions that I've created. The floating point divide fails in cycle 30. At that point in time, I have allowed instructions 2 and 3 to complete. What is the potential problem there when the divide restarts? R1's value has been rewritten, right? So the divide expects the value of R1 to be the value that was over here, right? But if I allow these instructions to complete, they have overwritten the value of R1, which essentially is a bad idea for that divide, because now it's going to work on some garbage value of R1, which it was not intended to work on, right? So that is also something that I need to kind of make sure that I find a workaround that as well, right? Sort of makes sense. So what I have sort of talked about are essentially the problems that come because of relaxing one simple assumption, which is my ALU stage takes different amounts of time, right? Which essentially leads to an out-of-order processor. But again, I have to make sure that I address all these problems so as to preserve what again? Program order. Program order is the most important thing that you need to preserve, right? Because you have the problem that you want to solve, and you have to solve it in a certain way. All right. So now let's take a look around how can we sort of solve some of these problems, and then we'll take a look at the last problem that we talked about there as well, right? So we talked about how you can deal with writes to the register file by increasing the number of ports. You can deal with the write after write hazards by detecting the instructions during the decode stage. And oh, actually, we didn't talk about this, right? So one of the ways of handling write after write hazards is detecting the hazards during instruction decode and stalling the later instruction, right? So can, okay, what do I mean with this over here? So let's take an example of a write after write hazard here as well, right? Write after write hazard is okay. Where did I put the chalk? Okay, there it is. All right. A write after write hazard is where I have write to R1 followed by another write to R1. So this is a write, this is also a write, right? And now what I'm saying over there is that we need to detect this particular write Turing hazard and stall the later instruction. What is being meant by that over there? So I have instruction 1 that writes into R1, and I have another instruction that writes into R1 again. R1 completes? Okay. So the second one? Yes. Right. Yes, that is true. That is true, but that can potentially happen, right? And in situations like that, what you have to detect is what I'm saying over there, right? So if this was, let's say, an integer add that we talked about before, right? And this was a divide, what essentially I have to do is essentially detect that there is a write that's going to happen by an integer add over there and make it stall until that first write has actually completed, right? So for example, going back to the earlier example where this writes 30 over here, this writes 55 over here, right? And there is another instruction that tries to read something from instruction or from register R1. What is the value that it should expect? Sorry? What is the value that it should expect? 55. All right. So is this a write read after sorry, write after write hazard? Huh? Is this a hazard actually? This is an integer add. This is a divide. Is this creating any problems over there? Huh? So if there was a read instruction where? Okay. That will cause problems, right? Yes. So that will cause problems as well, right? So what is the easiest way of avoiding this sort of a situation to happen is what's written over there, right? So the easiest way is to make sure that this writes first and that this writes second, right? And what we've talked about before is essentially take this instruction, make sure that it waits until that first instruction has actually completed before it can actually write into register R1. And that will make sure that that sort of solves our problems, right? So again, let's move forward a little bit and try and see what are the various ways in which we can sort of solve some of these problems that we have talked about, right? Okay. So what we are going to talk about now is essentially an out-of-order processor implementation that is going to solve some of these problems, right? So this is a very sort of a high-level conceptual diagram of what it's going to sort of look like, right? Before I sort of try and explain what these different boxes over there essentially mean, is let's talk a little bit about how can we make sure that the instructions that follow certain instructions only get the results from the right set of registers. Right? So what we've talked about so far, essentially, there are a lot of the, problems are actually being created because either somebody is writing into something later than they are actually supposed to, or somebody is, or some instruction, somebody in this case, some instruction is actually reading or trying to read from instruction that potentially might be overwritten by another instruction because it's either finishing earlier than it's supposed to, right? So one of the ways of easily avoiding that is essentially just buffering the results of the instructions, right? So if you want somebody to sort of get the right set of results in the meantime, while somebody else is keeping that resource busy, the easiest ways in which you can do that is create a buffer, right? So let's say I'm instruction. I am going to produce a certain result that essentially a lot of the instructions that follow me are going to depend on, right? I cannot write into my intended destination register because there is that long-standing divide that essentially has to write into that register, and it's going to write into that register a little while into the future. So the best way for me to create a situation where I can complete as well as write that result that I'm going to produce is to write into a buffer and convey that information to all the instructions that are going to follow me, right? So I am instruction, I proceed a result, I don't write into the register that I was intending to write into, which is register R1, right? What I do is I create this temporary buffer or a temporary spot somewhere in the middle, and I say, okay, rather than writing it into R1, where I was actually supposed to write, I'm going to write into this temporary register T1, right? And then everybody who is sort of following me and needs the value of the result that I'm going to produce, I'm going to tell them, okay, this is where you are going to go and get your result from, right? That kind of makes sense, right? And that is essentially sort of one mechanism by which we handle a lot of sort of these problems, right? And then let's take a look at what essentially is known as a very simple implementation of register renaming, right? And then let me walk through it a little bit, and then we'll figure something out. So changing the representation of what our pipeline kind of looks like, we'll take some of the structures from before and add some more structures, and then I'll sort of explain things as we move along, right? So in this stage over here, we have branch prediction, instruction fetch, and again, this does not reflect all the 5 stages of the pipeline that we had seen before, but only some of them, right? So we have branch prediction and instruction fetch, and again, branch prediction is something that that Biswa is actually going to talk about in the next lecture. Then we have this box over here, which is known as the instruction fetch queue. Then we have these new boxes, which is essentially reorder buffer and issue queue over here. Decode and rename. So what used to be a traditional decode stage is now going to be called decode and rename. You have the register file over here. You have the different execution units over here, right? And the way we were processing instructions before was essentially it was fetched, it was decoded, executed, a memory stage, and a write back stage, right? Now, because of the problems that we have seen happening so far, we are going to change the pipeline so that we are adding sort of more or more structures in the pipeline so that we can get rid of the problems that we had talked about before, right? So okay, so let's see how does this actually work. There is this instruction fetch queue, right? What do you think is the function of the instruction fetch queue over here? Okay, let's go back to our in-order pipeline, right? Instructions were being fetched. How many instructions were being fetched in an in-order pipeline at any given point in time? When you went and said fetch, how many instructions were being fetched over there? One instruction at a time, right? Because you really didn't have space to store anymore. What I'm saying over here is I'm going to fetch more instructions, more than one instruction at a time. So rather than fetching one instruction at a time, I'm going to make this bigger structure that can, let's say, fetch 16 instructions at a time, right? If I'm going to go to memory once, I'm going to fetch 16 instructions. Does that help me at all? Yes. Okay, so in order to find out the dependencies, all right, how does that help me? So I find out the dependencies, okay, but what is it that fetching multiple instructions is going to sort of tell me? And our overall goal is to improve throughput, right? That is our overall goal. We want to increase throughput. Okay, so you are almost on the right track, right? Throughput will be increased. Okay, how? So what are the opportunities that fetching more instruction at a time is going to provide me to increase throughput?
Somehow
Okay. Right. So almost correct, right? So let me try and rephrase that, and feel free to disagree, right? If I fetch more instructions than one, and I being the hardware, have the ability to sort of look through all of these instructions and say, well, which are the instructions that I can potentially execute in parallel, right? By either finding independent instructions, so there could be a whole bunch of instructions over here that are independent, right? So then if there are no dependencies between them, and I have enough execution units to schedule them onto, I can just say go execute, right? So if all of these instructions, and again, forget about what these are called over here for a second, but if all of these instructions were potentially independent and I had 5 independent execution units, I could have just said go run, right? And then potentially, assuming no dependencies, I could have completed all of them in one cycle. Best case scenario, right? But again, that's potentially not going to happen because there are dependencies, and then there are all these problems that are created because of the assumption that the ALUs takes different cycles, right? So we are going to try to find ways to overcome that as well. But fetching multiple instructions at least helps us figure out how many independent instructions are there, what are the instructions that have dependencies, and how can we avoid those dependencies, right? Or how can we sort of work our way around those dependencies, right? Okay? Yes?
You mentioned that the instruction fetching after model processing is taking a lot of instructions together from the previous whole set. It is taking a part of it, and then again it is checking for dependencies, and then it is trying to execute it, reorder and execute it.
Right.
But why is it checking again? Because the compiler did that step already, right?
Right. Absolutely. Okay. So I'll get to that, right? That's actually a good question. Somebody wants to take that? So compiler has already checked for dependencies. It has created code that has these dependent instructions sort of taken care of, right? So why do we want to check for dependencies over here again? Anybody wants to take a shot at that? That's actually a very good question. Yes? Okay, that's one part of it. What else? Okay. Right. So there are, anybody else wants to take same thing? Okay. So it's again the same thing, right? So what are the registers that the compiler sort of can use? Right? So there is this concept of the logical registers, right? The registers that are exported by the hardware that the compiler is supposed to use to create the set of assembly code that it actually does, right? So let's say I have an instruction set that exports registers R1 to R32. Now when the compiler is taking that C code and converting that into assembly code, it will just use registers R1 to R32, right? But I could potentially have more registers internally. Right? I could have 64, 128 registers that I could potentially use, right? The compiler is not aware of the fact. I being the hardware, I actually know how many registers I do have. Right? So I could potentially use those registers to reduce or remove some of the dependencies that potentially can be removed. And let's walk through a quick example over here, and things will hopefully be more clear. Yeah, I don't know. Actually, that's a good question. Why not just expose all the registers to the compiler? Is there anything wrong, right, in that?
In that case, the programmer will use all those registers for the execution.
Okay, but isn't that better than? Huh.
The programmer will again use all those 64 registers.
Uh huh.
Execution will be same as it was.
So what is the problem that is not going to be solved by exposing all the registers? The legacy code has been? So okay, so let's say I have I have a code that was written earlier. So initially, I had 32 registers that that my architecture was exposing. Now it's exposing 64. That problem is not going to be there anymore, right? I mean, if my legacy code used only 32 registers and the new set of, huh? Do I really need to decompile it? Okay. So if my legacy code used only 32 registers. Now I actually have 128 registers. Is that actually true? So if I'm increasing the number of registers from 32 to 128, everything else remaining the same, assuming, wouldn't my old code just run? Right. So we haven't gotten there yet, right? So we haven't gotten to the rename part yet. But if the case was that if I am using, if I had 32, now I have 64, now I have 128, I really don't need recompilation, right? Okay, yes.
I think, sir, the latency of each of the, say, stage in the pipeline doesn't have to do with compiler. Compiler doesn't know, say, it just rearranges instruction as per dependency.
Yes.
And without knowing the exact architectural latency of each stage in the pipeline.
Right.
So it cannot, say, reorder in terms architectural specifics.
Okay, so that's also a valid point, right? So architecture or the compiler knows that there is a dependency between this instruction and this instruction in terms of producer consumer, right? This is the consumer, this is the producer, but it doesn't actually know whether that producer is a multiply or the producer is a divide or the producer is an integer add. I mean, it knows, but it doesn't actually know the latency. So it can take a best guess scenario, right? I mean, it knows that on an Intel, Skylake floating point, just to pick a number, takes 50 cycles to process, whereas on an ARM something, it takes only, I don't know, 28 cycles to process, or something of that sort. So that is the information that the compiler doesn't have. That is the information that only the hardware has, right? So when your instruction has been put into the pipeline in the decode stage, assuming all the operands are ready, it knows that that divide or that multiply is going to take that long. Anyways, that's kind of beside the point, right? So let's take a look into how much time do I have left? 1 hour. Okay. Do we have a break in the middle? Okay. So let me go through that, and then we'll take a quick bio break, and then we'll come back. Okay. So the idea is this. Now I have this new unit that I have introduced over here, which is known as the instruction fetch queue, which fetches more than one instruction, because again, you have to keep in mind what my overall goal is. My overall goal is to increase my throughput as much as I want, which essentially means that, first of all, the easiest way of doing that would be to find the number of independent instructions that I can. So if I have a large window of instructions that I can look at, I can find a larger number of independent instructions which I can potentially process. So that's one way, right? Now I have these extra units over here, which is essentially the reorder buffer and the issue queue. So why are these units being introduced is the real question now, right? So remember what we talked about was buffering of the results beforehand, right? We talked about how if there are an instruction that's completing before a long-standing instruction and trying to write the result of that instruction into a register file or a register, and there are instructions that are depending on that, what I can do is I can buffer the results of this particular instruction over here is essentially what is happening in the reorder buffer, right? So let me sort of go through this example, and hopefully things will become a little more clear, right? So we have this instruction fetch queue where you fetch a number of instructions. In this case, there are only 6 instructions, but potentially you could have 16, 32, 64 number of instructions over here. Now, this is essentially just a pseudo representation of an add. So it takes registers R1 and R2 and writes a register or writes a result into register R1, takes R1 and R2 in this case, or R1 and R3 in this case, and writes a result into R2. Similarly, you have a branch, then another couple of adds, right? Okay. Now, are there real dependencies in this set of instructions? So what about instruction 1 and instruction 2? Is there a real dependency in this case? Right? There is a real dependency in this case. Now, in order to avoid some of the things that we had talked about before. What I'm going to do is anytime I produce a result and want to write into a register, what I'm going to do is I'm going to always say, rather than writing into register R1 over here, just take a temporary register. Everybody who wants to write your result into some destination register, rather than writing into a destination register, just take a temporary register, and assuming, again, I'm sort of talking about this abstract case where I have a lot of free registers lying around. Let's just assume that for fun. I have this register that's lying around. Put your result in that register. Don't write it to where you are supposed to do or supposed to write, which is R1. Just put that result in a temporary register, and that is essentially what I'm going to call as renaming. Right? So what I'm going to do over here is that I take the registers R1 or the value in the registers R1 and R2. When I have to write into R1, right? This was where I was supposed to write into R1. Rather than writing into R1, I'm going to write into a temporary register T1. Right? Okay. So now the next instruction is supposed to read the result of R1. Now the result of R1 after this instruction has been executed is sitting in T1 over here. Right? So again, I have fetched all these bunch of instructions. What I'm going to do is I'm going to rename these instructions such that every time I have to write a result somewhere, I don't write into that particular register. I write into a temporary register. So again, I have to write again into R2 over here. I don't write into R2. I write into this temporary register T2. Right? Okay. But I have to make sure of one thing. So there was a true dependence between this instruction and this instruction over here, right? Is that true dependence being preserved in that renaming over there? Right? So it was reading or writing into R1 and reading from R1 over here, this instruction 2. Now it's reading, this instruction 1 is writing into T1, which is, let's say, temporary register 1, and and this instruction is reading from T1. So that true dependency has to be preserved, right? And that is actually being preserved by register renaming over here. Okay. So every time and similarly, we can go through this example, right? So this guy reads a register of result from R2, which is being produced over here. So this is renamed to read T2, which is being produced over here. Similarly, now you have R1 plus R2, so you have T1 plus T2 because true dependencies, right? They have to be preserved. Similarly, over here as well, right? So you have T4 and T2 that is being written into T5. Okay. Now, that is all well and fine, right? So one thing that register renaming has got us is some of the dependencies that would have prevented us from scheduling instructions beforehand are now gone. Can somebody give me an example of 2 instructions from this set which would not have been scheduled before, which can now be scheduled because I have kind of done this fancy renaming operation over here? Sorry? First and the last one. Okay, that's a good point. Why? Right after write dependency, right? So initially, I mean, this was not a true dependency beforehand, but now in this case, if you look at this instruction and this instruction, because it's only working with the set of logical registers which were being exported by my architecture over here, there is a write after write dependence between these 2 instructions, right? But if I look at the 2 instructions over here, there is no such thing. Right? So that write after write dependency has actually been eliminated because of this instruction renaming that has happened. Right? So that's one part of this entire exercise. The second part of this entire exercise is this reorder buffer. Right? So what is the function of the reorder buffer over here? So again, I'm going to go back and harp on this need for preserving the program order of the program. Right? So essentially what that means is the instructions are supposed to finish in a certain order in which they are determined by the programmer to finish in, right? Now, when an instruction is fetched, and again, these instructions are fetched, these instructions are in program order, right? So this is supposed to happen before this, which is supposed to happen before this, and so on and so forth. Now, when I decode an instruction or decode and rename in this particular case is essentially I place them in the same order, in the program order, in the reorder buffer. right? So essentially this instruction is placed over here, which essentially means that this instruction's temporary result is going to be placed in T1. This instruction's temporary result is going to be placed into T2. This instruction's temporary result is going to be placed into T3, right? And again, in this particular case, this is a branch instruction, but again, this sort of high level renaming that I'm trying to do, I'm just saying that every instruction that comes in takes up a spot here in the ROB. Now, this was good for these two instructions because they are actually using up this temporary registers T1 and T2, but in this case, this is a branch instruction. It doesn't really need an output register, but because I'm making the assumption that every instruction that comes in has to take up a spot in the ROB, and that spot comes in with a temporary register as well, right? So that spot is being taken up here, but temporary register T3 is actually not being used at all, right? So in this case, this takes up this spot over here, uses up the temporary register, not for really anything useful. So that's why over here, the registers are actually being used T4, right? So the result of this instruction is being written into T4, and that's why you have renamed it to have T4 over here, okay? Okay, so the point that I'm trying to make here is that you have every instruction that is being decoded and renamed also being provided a space in the reorder buffer in program order, right? Again, I'm going to sort of emphasize that one more time. So these instructions are in program order, and what that essentially means is that, okay, so in an in-order pipeline, the program order was inherently preserved because instructions execute one after the other. What we can do in this case is we can allow the instructions to execute out of order, but complete in order, right? So again, I'm going to repeat that for effect. What I can allow in this particular pipeline case is for instructions to complete or to execute out of order, but for the pipeline to commit those instructions in order, right? Which essentially means that I can do these fancy tricks of buffering the results of these operations at these temporary registers, right? So again, so I have fetched a whole bunch of instructions. I have decoded those instructions, renamed those instructions, and put them into the issue queue over here. I have also made sure that every instruction that has been fetched and decoded gets a spot in the ROB, and that spot is given to it in program order, right? We are here up until that point, okay? Yes?
So, suppose the dependent instructions, like they are getting decoded and renamed, right?
Okay.
To avoid this kind of hazard, like right after right or read after right.
Sure.
So, if I have an independent instruction,
Uh-huh.
does it essentially need to be renamed? Because I don't need to, but it will not cause any errors, right? I can easily use them in a pipeline, I can just execute them. So, does it need to be renamed also and assign the place to the reorder buffer if it is an independent one?
Yes and no. Okay, so there are two parts of the question, right? One is, does it need to be renamed, and does it need to have a place in the reorder buffer? Okay, good question. So let's debate that. Does it need to be renamed? How many say yes? Does it need to be? So an independent instruction, let's say there is a sixth instruction over there, which essentially is R10 is written with the results of R15 and R18. That's an independent instruction, right? Does it need to be renamed? How many say yes? How many say it needs to be renamed? Nobody says? Okay, 1, 2, 3, 4, okay. 4 people say, how many say it doesn't need to be renamed? All right, so everybody else is on the fence. So it should either be named or it should not be renamed, right? Okay, so why do you think it should not be renamed? People who took the stand about not renaming it. Why should not it be renamed? It's an independent instruction, it should not be renamed. Why should it be renamed? Sorry?
To save the intent of the program. Like we are going to commit in order.
Huh.
So we are essentially looking at the reorder buffer and then committing.
Okay, but this in the, let's say I have only 10 instructions in my program, and again, very hypothetical situation, right? The 10th instruction is independent of everything. Can I not just commit in out of order? Like, did not be the first instruction that I ever execute. I'm still not changing anything else, right? Because the original or the instruction that was the last instruction is going to write into R18, for example, right? And nothing is ever going to read R18 or touch R18. So if I execute it last or execute it first is exactly the same thing. Why could I not just do that, right? I'm asking, why? Anybody wants to sort of take that? Right. Okay, so there are two things, right? There is execution and then there is a commit, and we'll talk about commit, right? So let's go back to your question. What's your name again? Gaurav. So Gaurav's question was whether an independent instruction needs to be renamed and whether it needs to have a place in the ROB. And I'm going to contest that the answer to both those questions is yes. Okay. It's yes, it needs to be renamed. Yes, it needs to be provided a space in the ROB. Now, can somebody give me an argument in support of what I have just said about? Okay. 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 So what Newton said was essentially is correct in terms of providing it a space in the ROB, because see, hardware likes everything to be exactly the same in terms of the sequence of steps that have to be followed, right? So if I make a choice that, okay, this instruction will be renamed and this instruction will not be renamed, that essentially means I need to put in more logic to handle both these cases, right? I need to say, well, okay, this instruction should be renamed, and then I have to check whether this instruction should be renamed or not. Then this instruction should not be renamed, and then I have to check. Too much work, right? So it's much easier to say, well, every instruction that comes into the pipeline is going to be renamed. Independent or not, it's just easier that way. So that's the answer there. Yes?
What is the point of optimizing the part of the code seeking for dependencies of instruction fetch queue? If we are not even solving the dependencies and independent instructions and executing them in the same order, like how we are executing dependent, then what is the point of checking for dependencies the first time?
Right. So okay. So that's a good question, right? So does Gaurav, your question is sort of answered? Let me move on. Okay. Now we have only up until this point done almost everything has happened in order, right? Fetch was in order, decode was in order. I said, well, okay, everything in the ROB also has to be put in order. Where the hell is out of order happening, right? I mean, throughput and all of this. Where is the out of order actually going to happen? And you have a very valid point there, right? Everything has happened in order. I have introduced, I don't know, 2-3 more units over there, which is a lot of transistors. And now, I mean, what's the point? So after all of this, is there a point to any of this? That's a very good question. Sorry, what's your name again? I forgot. Kostov. Kostov's point is actually the heart of this matter, right? We have been doing all of this for all this time. Now what?
The instruction fetch queue and the issue queue are not equivalent, right?
Instruction fetch can be, yes.
The moment you move to the reorder buffer, you've lost information about the order of the instructions. That is where the out of order is happening. The only place where you have any hint of how instructions are going through is the reorder buffer. You have a mapping
Okay.
between new and the old.
Yes. So I have a mapping between the new and old. All right.
So the issue queue is where you have actually separated the link between these instructions. Thereby you can send them whenever they give each other.
That is actually the point, right? So both the ROB and the issue queue serve different purposes, and we will just quickly talk about that and then take a break, right? So what the issue queue, so the entire point of this exercise was to find instructions that can potentially be executed either in parallel or write one after the other, so that we can sort of remove the dependencies that were not exactly there. Right? This, by doing all of this fancy renaming stuff, is essentially putting these instructions in the issue queue, is where we have potentially found out those instructions, right? So I talked about this instruction and this instruction. We said that these instructions potentially had a write after write hazard, so they could not be executed in parallel or right after one another, right? In this case, we have, by doing the register renaming, we have kind of removed that dependency. And that's where the parallelism comes from, right? So if I take a look at all the instructions that are present in the issue queue, then I can just take a look at for which one of these instructions are the operands ready, and I can potentially schedule them at any given point in time, right? So let's walk through this instruction set of instructions. And again, it's a very simple exercise, but in the first cycle, I take a look at this instruction, right? Can I schedule this instruction? Just the first one. Yes. Sure. Yes, yes. Yes, I agree, right? I agree. So in this case, the true dependencies have been preserved, and they have to be preserved no matter what, right? So, but in certain cases, and again, this is sort of like a contrived example, right? But in another case, if there was R1 being written into by R10 and R15 or something of that sort, right? So in that case, I could have potentially removed that dependency and just scheduled it one after the other, right? So again, the idea is that a lot of the idea of renaming is this: the dependencies that were not true dependencies but were still causing the instructions to not be able to be scheduled right one after the other have now been removed, and now those instructions can potentially be scheduled potentially in parallel, right? And the second thing is that the instructions, because now they are writing to temporary registers now rather than writing into R1 or R2 or wherever they were writing to initially, they are buffering their results until they can actually make their state permanent, right? So in this case, when this instruction potentially completes, it doesn't write into R2, it writes into T2, right? If something goes wrong, I could just discard the value in T2 and nothing is going to change, right? So again, when this instruction sort of completes, it writes this result into T2. So let's walk through this example one more time. Now I have this set of instructions that have been renamed, right? In the first cycle, can I schedule this instruction? Yes, no dependencies whatsoever. It writes and result into T1. In the same cycle, let's look at all the instructions that I can potentially schedule in cycle 1. This instruction I can schedule. Anything else I can potentially schedule? Which one? Can I? T2 is not ready, right? In this case, T2 is going to have some garbage, right? So it's going to be an invalid register at this point in time. So I can't schedule anything else in first cycle. Okay, so let's say at the cycle, so the next cycle, can I schedule anything else in the next cycle? This one, and anything? So, okay, when can I schedule this instruction? As soon as the result of T1 is available, right? So as soon as T1 is available, I can schedule this, right? Now, as soon as the result of T2 is available, I can schedule this, right? At this point in time, the results of T1 and T2 are both available, right? So I can schedule this, I can schedule this. So in that particular cycle, I could schedule both of these instructions to be executed, right? As soon as the results of this instruction are available, I can schedule this. And again, this is a very simple example, right? So for example, if I had an independent instruction over here, so let's say I had, let's say R10 plus R15 goes into R18, right? That would have been, let's say, renamed into T to something else. If that instruction was there, over here, would I have been able to schedule that in the first cycle itself? I could potentially have, right? So there was an instruction over here that was independent. I could have just scheduled that instruction to be executed in the first cycle, right? Now, execution and commit are two different things in this case. Now, when commit happens is when you say that, okay, I know for a fact that nothing else is going to go wrong, which is essentially an exception is probably not going to happen, right? All my divide by zeros have sort of been taken care of. My branch is not going to be mispredicted, so I don't have to squash all those instructions on the mispredicted branch, right? So when I am absolutely sure that nothing wrong is going to happen is when I say, well, okay, the results that are there in T2 now should be copied over into R1 and, or sorry, the results that are there in T1 should be copied into R1 and I'm going to make this state permanent, right? So that is essentially what is known as the commit process. And in this very simple example, when this instruction completes, the results are there in T1. The instruction is at the head of the ROB. It says, well, okay, I can make the changes permanent, right? So anytime an instruction wants to complete or wants to commit, which essentially is saying that it wants to make its architectural state permanent, it's only allowed to do that when it gets to the head of the ROB, right? So this instruction commits, makes its changes permanent, and then leaves. The next instruction to reach at the head of the ROB is this instruction. The next instruction to reach the head of the ROB is this instruction, as and when instructions commit, right? So when I'm making the changes permanent, I'm doing that in program order, because remember, the instructions got into the ROB in program order. I'm still executing instructions in parallel, right? So there was a cycle when these two instructions were scheduled in parallel, and the larger window you have, the more instructions you can potentially schedule in parallel. So I have sort of decoupled two things. What I have done is I have this execution part over here, and then I have that making the changes to the architectural state part over here. I have decoupled these two things. I can execute a lot of things in parallel, which essentially increases my throughput, but I'm still committing changes in program order, right? So which essentially preserves the sequence of instructions that needed to be followed. Okay, so let's take a quick break here, and we'll reconvene back in 5 minutes, or 5 minutes. Get back here in 5 minutes, and then we'll go another for half an hour or so. Okay. All right. So we'll come back here as 5 or 10:47, 10:50. Let's call it 10:50.